Hello and welcome everybody to the Van der Schaar Labs 2023 Open House. My name is Fergus Imrie and I'm a postdoc in the Van der Schaar Lab, and I'm going to be hosting today's Open House session. I'm delighted that you're able to join us today and hear us talk about what we've been working on over the past year, what we've achieved, and also to highlight some of our future plans for where the lab's research is going next. Before going any further, I want to begin with just a massive thank you. Your support of the lab is vital, and without this, it really wouldn't be possible to achieve what we've achieved. So the theme of today's open house session is the road to reality-centric AI. After an introduction and overview from Professor Van der Schaar, the session will consist of 9 talks, each lasting about 15 minutes per talk. Our talks today can be broken down into 4 categories. The first is about making AI and machine learning work in the real world. The second will cover next frontiers in personalized therapeutics. We'll then move on to talk about accelerating scientific discovery with AI, from pharmacology to physiology to physics. And we'll end with 3 talks on AI for human empowerment. But now, without any further ado, I turn over to Professor Mihaela Van der Schaar, who will open today's open house.
Welcome, everyone. Warm welcome to our 2023 open house edition. And as Fergus has said, today we will showcase some of the research highlights from our lab in the past year. But we are also planning to reveal our bold research agenda, which we call Reality-Centric AI. But more about this a little later. I would like to start by introducing you to our researchers, the postdocs and PhD students in our lab. And today you are going to hear from quite a few of them, and they will introduce themselves when they are going to give the talk. But I would also like to briefly introduce the new PhD students which just joined us in 2023, and that is Juliana, Cassia, Max, Nicolas, and Chiao. A warm welcome to all of them. And I would like to say that our group is truly diverse. Students come from a diversity of backgrounds: engineering, pure math, applied math, computer science, physics, economics, statistics, and even one person that has an art degree, but I would let you guess who that one is. I'm also extremely proud to say that our lab is very international and very internationally diverse. We have had over the years members from 18 different countries, and we really hope that we are going to have from many more, and we will work hard to recruit diverse, brilliant students in the years to come. I'm also absolutely delighted to say that in the past year, we had the great fortune of welcoming as member and advisor of our lab, Andrew Rashbas. Andrew is a professor at the Harvard Business School, and he's the former CEO of The Economist, Reuters, and Euromoney. But Andrew has a deep passion for AI. He studied many years ago AI, and he is glad to return to it. And we, on the other hand, we are extremely fortunate and very grateful to be working with him. So welcome, Andrew, to our lab and our group. It is wonderful to have you with us. We are also very fortunate to have amazing support in the form of excellent research engineers, Evgeny and Rob, our communications manager, Andreas, and Mihaela, who many of you know, who is our center coordinator and has tremendously helped with numerous events and really with shaping our lab. But let us now turn to research. In the past few years, we have seen significant advances in AI with the emergence of ChatGPT and more generally generative AI, advances in computer vision and robotics. And yet, we wonder, has AI truly transformed complex systems, such as healthcare systems? For instance, has AI fixed the issues with the NHS in the UK or enabled us to control the exorbitant costs of US healthcare? Can we alleviate traffic? And can we solve the energy crisis we are facing? Can we prevent the next financial crisis or a climate catastrophe? And have we really transformed education? The reality is that none of this has really happened. And we are not just a few breakthroughs away. Note, though, that I'm not saying that machine learning cannot solve these challenges or cannot play a role in these real-world domains. Rather, what I'm trying to say is that we need to think fundamentally differently about machine learning and AI and orient it towards the complexities of the real world. And indeed, over the last 20 years, our lab, with former generations of students and also with current students, has done a lot of work to build technology, especially AI, in all the domains that I'm highlighting here, from smart city to transportation, from communication networks to energy grids to economic and finance. But in the last 7 to 8 years, we mainly focused on AI for medicine and healthcare and AI for education. And we believe that solving these complex human-centric problems is our biggest task as AI researcher. And to do this, we strongly believe, as I mentioned, that a fundamental new paradigm is needed for AI. And this is why we have developed the Reality-Centric AI agenda. This manifesto is highlighted on our website very prominently when you come to our main website. And I'm just going to say a few words about it here, but if you have not read it, I would like to invite you to read it and provide us feedback. So what do we really mean by reality-centric AI? AI which aims to solve real-world problems. AI which operates effectively and accountably given the inherent and unavoidable complexities of the real world. An AI which empowers rather than marginalizes humans. And we have outlined in this agenda several pillars, some that are related to the model input. For instance, we recognize that AI needs a systematic way to identify how to model the world. We talk here again about the complexity of the real world and what features of this complex real world need to be considered when we model, for instance, a complex healthcare system like the NHS or clinical trials. A second pillar aims to develop AI models which operate with real-world data. And a third one, building learning systems which need a systematic way to determine which data to acquire. Then a second strand of our pillars focuses on the model output because we believe that AI models should adapt to changing circumstances post-deployment, as well as needing to respond to dynamic measures of success. They also need to respect human constraints, inclusively safety and trustworthiness. Finally, we need to engage with the entire model ecosystem. And AI needs to be designed in a way in which considers when and how to communicate with humans and support interoperability with other models, not necessarily AI-based, components and systems. Again, much more about this research agenda in the future. And if you want to read about it, we invite you to take a look at our website where this manifesto paper is highlighted. Today, on purpose, I have selected several strands of our recent research that are very much on the road to this reality-centric AI. And we are going to talk about making AI and machine learning work in the real world and various aspects associated with it. We are going to talk how we engage with the world of personalized therapeutics such that we transform personalized medicine. We are talking about how we can accelerate scientific discovery from pharmacology to physiology to physics. And finally, the exciting topic of how can we build AI that empowers rather than marginalizes humans. Let me tell you a few highlights of our research in the past year. First, we have been very successful at developing cutting-edge research in machine learning, and this has appeared at several top conferences in our field: NeoRIPS, ICML, iClear, and AIStats. And you can read all these different papers on our website. Also, I'm going to highlight now just one of the many aspects in view of time. And an area in which we have worked very hard over the past year was pillar 2 of the reality-centric agenda, which is building models which are designed to operate with real-world data. What do I mean by real-world data? Data that is usually incomplete, unavailable, biased, full of errors and noise, may be gathered with delay, is costly to acquire, like for instance in a clinical trial, is subject to privacy and many other constraints, and it can change as circumstances change. For instance, in the case of COVID, many things have changed over time in the type of data that we obtain and need to consider. And two strands of the research that we have spent a lot of time this year on are data-centric AI and synthetic data, and this is the first set of topics you'll hear today. But we have not only done that, we also have developed a significant set of resources, and together with Nabeel Seedat, a PhD student in the lab about whom you will hear more from today, we are giving, together with Isabelle Guillon, which is the Director of Research at Google, a tutorial at NeoRIPS 2023. And this is an example of how we are trying to disseminate beyond our research lab the research that has happened in the lab. In addition, we have given several other tutorials, for instance, at IJCAI 2023, again, together with Nabeel, and at AAAI 2023, together with Zhaoji and Rob. And that tutorial was on synthetic data. This tutorial on synthetic data can also be found online on our website under the tutorial banner. We also organize workshops, and it is the second year in a row that we organize at NeoRIPS 2023 a workshop on synthetic data, and this became stronger and stronger every year, and many of you, our sponsors, are participating in it as well. We also have continued our engagement sessions. For instance, we have already for 3 years Inspiration Exchange. We have more than 30 sessions online, and they contain engagements with machine learning students as well as professionals. We have a lot of discussions with industry, and we hope that many of you are going to join us in these sessions and discuss with us. In addition, the sister session, which is focused on revolutionary clinicians, revolutionizing healthcare, is also in its 3rd year, and we have more than 650 clinicians from 5 different continents discussing with us how the AI needs to evolve to be empowering for clinicians and patients. Also, we are excited to continue less regularly, but still steadily, our session dedicated to inspiring female students and young professionals to join the world of artificial intelligence and machine learning. And we call this session We Create. And again, many of you have joined us in previous sessions, and these sessions are online on our YouTube channel. If you want to read more beyond what you are going to see today about the impact our research in AI is having on numerous clinical areas, please take a look on our website under the heading Impact. And another impact of our work comes not only from publications and collaborations, but also through software, open source software that we have developed over the years. And this is both in the form of software that comes together with our papers, for instance, at NeoRIPS, iClear, ICML, but also software which is developed at another level by our machine learning engineers. And you see here some of these very stable software suites that are really quite comprehensive and address a variety of issues, from automated machine learning to imputation, to interpretability, to synthetic data, to data-centric AI, and many more such packages, open source packages, will be made available in the future. Also, we have a very symbiotic tie with the Cambridge Center for AI in Medicine, the center that I am directing. And while our lab is focusing on developing cutting-edge machine learning and AI models, and we keep, of course, a focus on healthcare and education, but our main focus is on developing cutting-edge breakthrough AI. In CCM, we are taking these tools and applying them to specific, impactful medical and biological settings. And it is through this symbiosis that a lot of impact is happening. I would like to highlight just a few of this impact with our Cambridge Center for AI and Medicine clinical experts. For instance, in a collaboration between one of the members of CCIM, Dr. Richard Peck, together with Alex Chan, important piece of work has happened on synthetic model combination. But what's very exciting is that this work also included one of our sponsors, Dr. Megan Gibbs from AstraZeneca. Other works, together with Professor Andres Flotto and Yuchao Chin from our lab, has focused on cystic fibrosis. We also, together with Fergus and another clinician from the Cambridge Center for AI and Medicine, Professor Eoin McKinney, we developed automatic tool for diagnostic and prognostics risk scoring, which enables clinicians and any other medical professionals to build risk scores at the push of a button. This is a software called Autoprognosis. And finally, let me highlight a rather recent and exciting collaboration, work with another clinician associated with our Cambridge Center for AI in Medicine, Dr. Thomas Callender, as well as Fergus, on really how can we use cutting-edge AI to do much better population-level screening for lung cancer screening in the UK. That being said, I'd like to conclude by saying that I hope that you, our sponsors, will engage with us so that we can together deliver the promise of machine learning and AI to have a major real-world impact that benefits society and humanity. I hope that you, together with us, will be part of this research agenda, and that we together are going to solve the biggest challenges and transform the world for the better. A big thank you to you, all our sponsors, for this research. Thank you.
That brings us now to the first set of talks. And so I'll just like to briefly introduce our first three speakers of today. Under the topic of making AI and ML work in the real world, we first have Nabeel Seedat, who's going to speak on data-centric AI, followed by Boris van Breugel, who's going to talk about reality-centric testing of AI and machine learning models. The third talk of this first mini session will be by Alicia Curth, who will talk about individualized treatment effects, and in particular about competing risks and time series estimation.
So hi, good afternoon, everyone. My name is Nabeel Seedat. I'm super excited to be talking to you today about a data-centric AI lens and how we view this as enabling robust and reliable AI in the real world. So as we all know, data is fundamentally the fuel for machine learning, but when we take machine learning to the real world, challenges in real data are often quite abundant and particularly quite impactful for machine learning systems, especially if we want them to be robust and reliable when we take them to the real world. And to give you a sense of what these challenges may be, We might have mislabelings in data. For example, we might have incorrect disease labels assigned to individuals. We might have mismeasurements, for example, incorrect biomarkers being measured for specific people. We might actually have noisy data from measurement devices themselves, or even from human annotation itself. We could also have errors propagating when we start chaining systems together from one system to another. But this also goes beyond just purely data quality itself. We might actually have underrepresentation in data that we really want to account for and identify from a perspective of fairness of machine learning. We also want to account for things like distributional shifts in the data. And all of this here, you might be thinking is just in a healthcare scenario, but this fundamental issue of data itself really goes beyond healthcare, goes beyond even tabular data settings, and even more fundamentally to machine learning in general. For example, we might have large-scale image data sets where images are largely quite blurry, and we feel that these sorts of images actually might affect a computer vision model trained on such data sets, and we want to audit them. Or additionally, we might have a language data set where we actually have text of one sentiment, and we've had human annotators annotate such a data set and have incorrectly identified the sentiment. And how do we identify this in very large-scale data sets in vastly an automated manner? So the question is, how do we handle all these huge challenges when we go to the real world? So right now, the current approach in machine learning is what we term model-centric AI, where data is really considered somewhat of a fixed asset, where data is just drawn either from some sort of SQL database. We might pull a CSV off Kaggle. We might take some large-scale image or text repository, and then we take all of these very fixed data sets and train a machine learning model, where our focus is largely how do we iterate on the model? How do we build a new architecture? How do we do a new loss function or an optimizer? And we hope that that's a way to make our models really highly performant in the real world. And this is a very important aspect of machine learning research and one that really needs a lot of focus. But purely a focus on this really neglects the importance of the data feeding these highly performant models. And that's where data-centric AI starts to want to put this focus on data iteration, from data acquisition to cleaning, auditing, and generation. And how can we do this in a very principled and systematic manner using machine learning? And then we consider models could be highly standardized, from neural networks to boosting transformers, etc., which have been developed from the model-centric aspect. So just to anchor everyone with the definition, we feel that data-centric AI really encompasses methods and tools to systematically characterize, evaluate, and generate the underlying data used to both train and evaluate machine learning models. But now that we have this very concrete definition, the challenge with data-centric AI is we understand it's a very important area, but as a very nascent field, it's often quite hard to engage with, both from a research perspective, but as well for industry practitioners. Because we have no standardized processes for data-centric AI at the moment, we have no guide of what are necessary data-centric considerations we should consider from the first place. And additionally, what are suggested tooling or opportunities that we have from a research perspective? So over the last year, we've developed something to try address this first consideration, something called DC Check, which is a data-centric AI checklist. And this was developed together with Fergus and Mihaela, and you can find more on the link on the lab's website. But to give it just a high-level intuition of what DC Check really does, is it tries to look at data-centric AI and how data plays a role across the entire machine learning pipeline, all the way from data to training, testing, and deployment, and really tries to give people that roadmap to how do we elicit what considerations there might be at each stage, but also provide suggested tooling as well as research opportunities for the community to try address on our path to this really reliable machine learning that we really want. And the lab, we've actually developed a variety of tools across this whole diagram that you can see on the screen, from the data side to the testing side, as you'll see from Boris later, to the deployment side of actually identifying from an uncertainty perspective when you might not trust samples at deployment time. But just in the essence of time, given this field is quite big, today I'll simply be focusing on data quality evaluation as an area. And what this means is, under data quality evaluation, there's an area called data characterization. And the goal is, how do we curate data sets for high quality in the first place? And it's that auditing and curating data sets, specifically, especially at scale, is often quite hard, it's quite time consuming, and requires a huge amount of human effort. And we ask, how can we do this in a much more pragmatic way and much more systematic and principled manner? And what data characterization really fundamentally does, it takes the idea that not all data points in a data set are equal to one another. And the goal is to assign a score to each individual sample in a data set. And on the basis of these scores, we then can start reasoning about which samples might be hard for models to learn, which might be ambiguous, which might be mislabeled, which samples are actually more learnable and important. And we use these scores as a principled way to make these value judgments on individual samples. And to just give you an idea of what these value judgments on individual samples and characterization can actually unlock, I first want to show an application to really anchor what this actually does. So on a previous paper that we've done last year at NeurIPS 2022 called Data IQ, I give you an example of how we might audit an image dataset. So we might understand that data has different samples, those that are easy, ambiguous, or hard. And from an easy perspective, we might find samples if we're auditing, for example, the Celeb A image dataset, which are highly clear images that we probably want to train a model on. However, what Data IQ could somewhat unlock from a data characterization perspective is what are ambiguous samples. For example, a model might consider images of females with shorter hair are considered ambiguous, or blurry images, or those taken at strange angles. And what this really unlocks is the fact that we've got these intrinsic biases in data sets, and this allows a human being to actually see these biases, as you can see on the screen, and say, how can we avoid a machine learning model actually taking in and imbuing these biases that we actually don't want to have in the first place? For example, we actually don't want models to take any of these biases actually into consideration, but we first need to identify them in the first place. And finally, something like a hard example might be identifying things with incorrect ground truth labels. And there's a wide variety of data characterization methods that have been developed, including our own Data IQ from NeurIPS 2022 last year, but there's also a wide variety of methods in the literature as well. And the major focus of all of these methods has really been on the classification problem when we're trying to predict discrete outputs. And what we thought about over the last year is that actually regression is also really crucial, especially in the healthcare scenario. For example, imagine we want to do length of stay prediction of a patient in a hospital, or we want to predict some continuous biomarker of a patient, particularly maybe in a clinical trial. That's where regression becomes really, really important. And if we don't have data of this high quality, which might have these issues, we might actually not fit correct regressors and hence not capture the correct relationships. And the challenge is current classification approaches to data characterization simply cannot be applied because most of them actually operate on the discrete outputs on the probabilities from many of these machine learning models. So that's where we introduced triage, a method for characterizing and auditing training data for improved regression. And this was jointly done with Jonathan Crabbé, Xiaoxi Chen, and Mihaela. And we'll be presenting this at NeurIPS 2023. And what we really tried to address in this paper is what is the major challenge for regression is we really need to first establish a principled scoring metric. And we felt that actually the full information of any uncertain label lies in its probability distribution. And if we have this probability distribution, it allows us to then compute probabilities of various outcomes. The question is, how do we actually do this? And in order to do this, we need to address limitations of existing approaches. So for instance, point estimators from regressors simply do not allow us to compute this. If we are to do interval regression, for example, conformal prediction or any type of normal interval regression, we simply get an interval of a certain width reflecting uncertainty, but it still does not allow us to compute these probabilities. And while Bayesian methods do offer this to us, the drawback is A, we have to make certain assumptions, but additionally, we fundamentally have to change our regressors in order to accommodate this. And what we really want in this paper is how can we do this in a model agnostic manner for any regressor without having to even change our downstream regressor. And for that, we introduced triage, a pipeline approach for data characterization for regression. And I'll be diving into each of these components briefly. So the first is what we do is we formalize a principal scoring metric based on conformal predictive distributions. And to give a high-level idea, and you can take a read of the paper for more details, is conformal predictive distributions are a powerful model agnostic and distribution-free method. And what they allow us to do is produce an actual predictive distribution simply by virtue of how we work with the non-conformity scores which come with traditional conformal prediction. And by virtue of actually arranging our non-conformity scores in a specific way, we can interpret this output as a predictive distribution as it satisfies all of the properties of a PDF. Once we have this, we're then able to easily compute the probability that y is less than or equal to f of x, and this is what we term our triage score. But we don't stop there and compute it once off. What we then do is we say, the fact that models learn different samples at different rates through the training process. For example, some models learn samples quite quickly, while some samples are learned quite slowly through the training process. We actually compute this triage score and we analyze how it evolves over the training process, as you can see in the diagram there. You can see, for example, in orange, some of these samples actually converge quite quickly, whereas in green, some of the samples in their scores actually oscillate around quite a lot. And using this understanding of dynamics of training and how the scores change through the training process and the model learns them, we're then able to estimate which samples are likely underestimated, well-estimated, or overestimated. And on the basis of these, we can then do some downstream tasks with them, but we can also do something called data sculpting or filtering and then refit our regressors. And we show that in the paper, triage can help with length of stay prediction in the ICU, for instance, as an example. We show improved downstream performance. And we show that what's interesting is we can also use much less data, yet achieve also high performance just by virtue of filtering. Additionally, what's interesting is we go beyond just average performance. We don't just sculpt people on our long tails of the outcomes. You can see the results in the paper, but what triage does, we not only have better overall performance for average patient populations, but we also show specifically we benefit the tails and small subgroups, which is very important, not only in healthcare, but in areas beyond, such as education. We then say, all of this was in an IID setting. Can triage help us go cross-setting for deployment purposes? We might be in the United Kingdom, where we have a small target domain dataset, which is insufficient to train our regressor. What if we could sculpt a much larger dataset, but is actually fundamentally different from a distributional perspective? And the problem is, how can we do this with triage? And we say that we can use a small data set from our target domain to calibrate and help us to sculpt a much larger data set. As in, we can select which patients we actually want to remove from a much larger source data set, train our model, and then we can transfer it to the UK, and it will actually perform much better than even just training on the UK alone. For instance, as you can see here, we achieve much higher performance to various other sculpting methods. But what's very, very interesting is we actually only require very few samples from the target domain in order to do the sculpting of this much larger domain from the United States. What else might you want to learn about triage just beyond just like purely performance-driven aspects? We not only show in the paper that triage is something which can enable consistent characterization for similar performing models, we also look at data collection itself, both from an aspect of which features might you want to collect next and might be both valuable to improve your regressor, but also if you have multiple data sets, how do you select which data set you should actually train your regressor on, for instance, if you generated multiple synthetic data sets. And finally, from a versatility perspective, we showed usability across a variety of different regressors, which you might use in practice. So if all of this was really exciting and all of these applications are something you want to bring to your own data, we wanted to introduce a package open source called Datagnosis, which was together with myself and Rob Davis. It really brings data characterization to your own data under a unified interface and API, where we bring 12 state-of-the-art data characterization methods, which unlock all of these applications, which I showed previously, and really bring them into an easy interface for people to use in a very much fit predict kind of paradigm. And what's also interesting, it can be easily extendable in a plugin style should your use case really demand some flexibility. And I'd encourage you please to take a look at it at the lab's GitHub and to play around with it. And really, we'd love to see what you do with it on your own data. If you really want to then learn more about data-centric AI beyond what I've just talked about on data quality on that much larger scale aspect, as I showed on the DC check slide, please, we'd love you to engage with either our IJK tutorial or the tutorial upcoming at NeurIPS 2023. We'd love for you to either join us in New Orleans for the tutorial or to reach out to us, because we'd love to share all of this information with you in much more detail. And finally, I'd like to thank my sponsors, the Cystic Fibrosis Trust, without which none of this research would have been possible. Thanks.
Yeah, I will be continuing a little bit from Nabeel's presentation on how do we actually do model testing in a reality-centric manner, and specifically how do we actually use synthetic data for that. I'll be presenting 3S testing, generating synthetic data from machine learning model testing, which was work by me, Nabeel, Fergus, and Mihaela. So before we go into the core of this project, let's briefly look at the motivation. So here there's an article where people showed how Google's medical AI seemed to be really good, but then actually in the real world it wasn't as good. So the problem is that model testing is inadequate often. So the aim that we have is to evaluate a model really well. So in this case, the medical AI, give it some test data. The problem so it's kind of similar to how you, for example, would test components in engineering. The problem, however, is that sometimes this test data is not good enough, like was the case for Google. So an example, for example, is this one, where we, this is a toy example, where depending on your ethnicity and your age, there might not actually be that many samples in our test data. So in the top right quadrant, there's only 2 samples, and then of course the variance of our estimate of how well the model will do will be very high. And in turn, we might actually think that our model does very well, but then actually it will do very poorly in the real world. Or in some cases, we might not have any data at all. So if we train our model on, say, American or UK data, and we try and roll out our model in a very different population, we have no idea how our model will perform. So we don't have any data from this distributional shift in that case. So what do we try to do here? We propose a paradigm shift away from just using real data for testing, but towards creating realistic synthetic test sets for machine learning model testing and probing. And the desired properties are twofold. First, we want granular evaluation. So, for example, like we saw in the beginning, we want to be able to test our performance on minority subgroups for which we might not have a lot of real data. And secondly, we also want to be able to kind of quantify the sensitivity to distributional shifts. So how would a model perform on an older population? So, or in a different country. So very much related to also what Nabeel was saying before. Of course, you might wonder, okay, but that's quite weird, Boris, because now you're telling me that you can generate synthetic data based on a real data set, and then the synthetic data will be more valuable than the real data. Yes, exactly, that's what I'm saying. And there's 2 reasons for that. The first one is that generative models can learn the distributional manifold. So a very simple toy example on the right side, we might see the top figure that's with red dots for one class and green dots for another class, and we see very few green dots. But there is actually a very clear manifold here, and a generative model can actually learn this manifold and thereby generate relatively realistic data for the minority subgroup, even though this minority subgroup doesn't have a lot of data. So you can use areas where you have a lot of data for, in this case, the red points, to actually model the green points. If you would, for example, in this case, evaluate the dotted classifier, the top real test data might give a very poor estimate because there's only very few points. So it will have a very high variance. In the bottom, that variance will be lower. Secondly, so the variance is lower, and we will also see this in our experiments. And this is also something that other people have shown, that synthetic data can help with model training. But again, we are looking at model testing. So we assume that the model is already given to us. So we propose 3S testing, which is accepted for NeurIPS 2023, which stands for synthetic data for subgroup and shift testing. So the solution is that we use deep generative models to create synthetic data sets with characteristics that we want. So for example, the minority subgroups or the shifts. Let's first look at the minority subgroup. So for granular evaluation, we might consider this data set. So there's limited real test data, And there's some groups, in this case, for example, the green people, for which we have very little data. We train a generative model on this that can model, it's often we use a conditional generative model for this. And then when the model is trained, we can actually give subgroup information and actually generate more data for these subgroups. So for example, for every group, we just generate more data. And then subsequently, as always, we just train our model. So in this case, we can, for example, evaluate performance for specific categories, say female or male, but we can also do intersections thereof. So for example, black and female, which of course in the real world will have it's much smaller. Intersectional groups are by definition smaller. You could also do slices of variables for numerical variables, so for example 75 plus, and you can also do points of interest. So for example, if you have a single patient and you want to know how well does the model do on this patient, very likely you don't have any real test data for exactly that patient. But using our model, you can at least generate very similar points and see how it performs. It's exactly the same for evaluating performance for shifts. So again, we train and tune a generative model, then we generate extra data with particular shifts. And for those shifts, we need a little bit of extra knowledge, as I will go into. And then we actually test the data on this shifted data. Of course, how we define the shifts is somewhat up to the user, but it's what we, for example, show in the paper is that you can, for example, have marginal shifts in which you assume that some variables change, like age might change from one population to another, or you assume that you see some data from the target domain, but very little, and you use that data to implicitly define the shifts. You might also know some high-level target statistics. So, for example, you might know, okay, I have data from the UK, and in the Netherlands, the age is 5 years older, and it's standard deviation of so much. You can use this information to define your potential shifts and to measure the sensitivity to these shifts. You might wonder, okay, but the synthetic data might have errors, and that's true. So we need actually confidence intervals for our test estimates. We use DGE for this, which is a paper we submitted at, we got accepted at ICML 2023, which quantifies the uncertainty of generative models using a deep generative ensemble. Deep ensembles have been used in the supervised learning literature, but we showed in this paper that you can actually also use it for generative modeling so that you can get these uncertainty estimates of the generation quality. I will not go into detail now, but definitely have a look at the paper. Look at some of the results. So 3S enables accurate testing for small subgroups with shifts and with confidence intervals. That's a quick summary. Let's look at some figures. First, we see if we look here at the yellow bars, the performance error, so the estimate error of our model on real subgroups. And we see that the error is usually slightly bigger for the small subgroups. So the pitfall of just the standard paradigm is that these small subgroups have, of course, a very high variance just because they are small. A baseline, model-based metrics actually don't do very well, also have a very high variance, and in some cases, very, very high. On the other hand, if you look at the green bars, they are much lower in general, and quite a bit lower than the actual test sets, so the real test sets. And then we also include 3S plus, which is synthetic data combined with the real data, which sometimes leads to even better results. If we look at the actual sensitivity to shifts without any prior knowledge, we also see that we do better. So here we plot the performance where we essentially shift the data set, one of the variables, and we shift the age. So we say, okay, what would happen if the age of the population is, say, 5 years older or 5 years younger? And we actually see that 3S gives very good estimates for how the performance of the model might shift in that case. MS and IS are two baselines, and we see that they are actually very bad, and that's mainly due to variance. So these results show that we can characterize model performance for possible shifts. So you might say, okay, the UK population is this age, but we know that in other countries it might be higher. Then we know how do we expect that the performance will change. Yeah, as you see, it's lower. It's almost lower consistently. When we see some data for the target domain, of course, we could do even better. In the previous figure, we didn't use any target data. We just characterized the performance. But here we actually know the target domain a little bit. These are results where we have a data set from the US, which is very big, and we then take a small data set from the UK, and we assume we see some variables. So in the right figure, we see that if we only see one feature in the target domain, we can not actually predict the accuracy of the model in the target domain very well. But the more features we add, the better we do. We are the pink model, and we actually converge to the target very quickly. If we would just use the real data, then of course we're not doing very well. And blue is again a baseline, but it doesn't converge to the right performance quick enough. On the left, we see that the actual model ranking is also much better preserved by 3S, which means we can actually decide to use one model over another model in the target domain based on the 3S characterization, and with baselines, we would not make the right choice. And then at last, let's look at the confidence intervals. And here we show some different methods. 3S case 1, case 5, case 10, which is the number of ensemble members we use. And we see that actually if we use 5 or 10 ensemble members, I won't go into details, but we actually get a very good coverage. The higher the coverage, the better, the more essentially the more accurate our confidence is. We also want a small interval width though, because if we would make a prediction of the model performance, but it's a very wide interval, then it's not very useful. And we actually show here that the interval widths are not that high for 3S, but they're very accurate. And the baseline MBM is poorer in both metrics. So then we come to the actual conclusion. We've seen that synthetic data enables accurate machine learning model testing, both for underrepresented subgroups. It's possible to do this because the synthetic data can capture something that the real data doesn't, and it has lower variance. Of course, this is not the end of it. We actually envision that synthetic data will play a much more major role in the machine learning testing paradigms. For example, you might consider automated model reports using synthetic data that can anticipate model failures in unseen populations or domains. At last, I'd like to thank the sponsors, for me, ONI UK, and for Nabeel, cystic fibrosis. Thank you very much.
Hi, everyone. My name is Alicia. I'm in the final year of my PhD with Mihaela, and I will be talking about individualized treatment effects in today's presentation. The goal in most of my work is to estimate the effect of a treatment on an individual patient. Basically, we want to answer the question, will a given treatment work for an individual patient, where we're learning from observational data, where patients are characterized by some characteristics, say age, gender, weight, and their treatment status. So whether they've received treatment, whether they didn't, and the outcomes that were observed with the associated treatment. And the machine learning literature has studied this problem quite a bit recently, but it has only focused on a relatively small subset of the problems that are possible within this space. In particular, there's been a huge stream on new methods for learning from heterogeneous effects from static data. So that the machine learning toolbox in this context is expanding rapidly and contains everything from meta-learners to trees, forests, neural networks, and Gaussian processes. More recently, some work, including lots of work from our own lab, has been on methods for learning from longitudinal or time series data. But this has almost exclusively focused on challenges arising due to confounding. And overall, most work in this space focuses on learning from historical data, where data collection and treatment assignment are not active. This year, we've kind of tried to go a bit closer to reality and have a new look at problems. And basically, as a kind of a year in review, well, when I say year, I mean academic year. So the last academic year in review, there are 4 papers that we did in this space, considering 4 different problems. The first one looked at static data, where we moved beyond standard outcomes to consider survival outcomes with competing risks in more depth. That was published at AI Stats earlier this year. The second one also focused on static data, where we looked at, because our toolbox is maturing, we should push our understanding of model selection more. That was presented at ICML. Then we moved to longitudinal data and argued that time brings more challenges than just confounding, and studied informative sampling in an ICML paper together with our visiting student Tone. And then finally, we considered data types and considered active data collection for adaptive clinical trials, also at ICML this year. Today, I only have time to talk about 2 of these papers, so I will be talking about treatment effect estimation with competing risks in the first part of this talk, and on treatment effect estimation from longitudinal data with informative sampling in the second part of this talk. So in the first part of this talk, I will be focusing on understanding the impact of competing events on heterogeneous treatment effect estimation from time to event data. What does this mean? In this work, we are interested in patients characterized by some covariates X, say age, weight, gender, and we're interested in a time to event outcome. What this means is, for example, we're interested in a cancer event, whether someone will have their tumor size exceed a certain threshold, for example, and when that will occur, whether it will occur early in time or later in time. And specifically, we're interested in the effect of a treatment in the setting, whether a treatment has an effect on delaying this cancer event from happening. This is a standard survival or time to event prediction outcome. And 2 years ago at NeurIPS, we considered this specific problem. Now, in reality, people can't only have events due to one condition, but there's so-called competing events. So for example, say we have an individual could also have a heart attack and possibly die. And if someone has a heart attack before they can experience their cancer event, this means that we cannot observe the actual outcome that we're interested in, because this event occurs before. Yet, in many medical applications where there are treatments, we are actually interested in the effect of treatments when there's both a main event that we're interested in and a competing event, such as a heart attack. So the question that we wanted to answer in this paper is whether we can use our standard treatment effect toolbox to estimate treatment effects in this setting. And I will talk a little bit now about why this is actually problematic. Even if we're considering the most basic approach, which is estimating heterogeneous treatment effects by comparing potential outcome predictions using a so-called T-learner approach. So basically by comparing the risk of the main event occurring by the end of a study without treatment to the risk of a main event occurring by a study with treatment, there's an interesting conceptual thing that happens because of the presence of competing events. In particular, say we're interested in patients with a specific covariate value X, and we observe a couple of them. So in the control arm, we see that we have 2 competing events occurring. We have 2 cancer events occurring. We have 1 competing event occurring, and 1 individual lives to the end of study. Now, imagine we have a treatment that immediately kills everyone, that induces heart attacks. So it has a very strong side effect of inducing heart attack. In this case, the probability of the main event occurring in the control arm is 1/2. And the probability of the main event occurring in the treatment arm is 0. So if we were to simply compare the outcomes in the 2 arms, we would conclude, well, this treatment is very effective at preventing cancer events. However, I'm not so sure if that is the definition of what makes treatment effective that we would want to be using in reality. So what we realized is that in this setting, in the setting with competing events, there's actually a conceptual challenge, and that is that competing events act as mediators of the effective treatment on the outcome of interest. And in particular, that there's therefore more than one heterogeneous effect of possible interest in this case. In fact, there are 3 different effects that one could be interested in the presence of competing events when looking at treatment effects. And I'm going to go through the 3 now. On the one hand, there's something we would call a total effect. That is the kind of effect that we just looked at on the previous slide in the previous example. That basically asks the question, what is the total effect of treatment through all paths? And that includes the paths that go through the competing event. So in the previous example, the fact that our treatment kills all individuals using through the competing event is on a total effect scale, a valid path of the treatment effect. To identify this kind of an effect, you only need standard ignorability assumptions with respect to the treatment. But the conceptual challenge associated with this is that it leads to possibly counterintuitive conclusions on the heterogeneous treatment effect itself. But to estimate it, you could simply use cause-specific predictions from time to event, competing event models. Another effect one might be interested in is a direct effect. And that is the effect of treatment in a world where the competing event doesn't exist at all. This requires very strong assumptions regarding ignorability with respect to both the treatment and the competing event, and conceptually kind of requires a world where competing events can be completely eliminated. So it requires a world in which we could say, well, imagine heart attacks don't exist. But I'm not sure if we can imagine this kind of world. But in case we are willing to make these kind of assumptions, we can estimate direct effects by treating the competing event as a censoring event and using a single event time to event model. A third type of effect is what we call a separable direct effect. A separable effect uses the assumption or asks the question, what is the effect of the component of treatment that acts only through the main event? Oh, sorry. And requires ignorability with respect to treatment and the dismissible component assumption. This kind of requires the conceptual assumption that you can decompose treatment into 2 components. And if you're willing to make all of these assumptions, it can be estimated, but it's not a byproduct of existing predictions, but estimable from cause-specific hazards. In our paper, we studied treatment and event-specific hazard estimation, which can be framed as a standard machine learning classification problem. And we try to solve the classification problem of those at risk today who will experience their event today. And if we write this in an empirical risk minimization form, we will see that from the observational data, we have a specific distribution of patient characteristics available. And we realized that when all effects are identified, the main learning challenge involved in this problem lies in covariate shift. That is, if different effects are identified, then different effects correspond to different conceptual interventions on the data generating distribution. When we're interested in total effects, we only have confounding induced shifts in our data. That is, if treatment propensities vary, there is a covariate shift. If we're interested in separable effects, there's an additional shift if the treatment effect on the competing event is heterogeneous. And if we're interested in a direct effect, there's an additional shift if the risk of competing event depends on covariates. In our paper, we then look at the theoretical and empirical effects of these different shifts and presented theoretical analysis using ideas from domain adaptation and empirical insights in the simulation study. But the main question we really wanted to answer in this paper is how much harder does the presence of competing events make the heterogeneous treatment effect estimation problem? And the answer is quite a bit. Competing events really bring conceptual identification and estimation challenges all at the same time. And we focused on very simple covariate shift mitigation strategies here, but there's a lot more room for technical innovation. So that's the first problem that we kind of considered in this year. And a second problem that has a related problem that we looked at next is accounting for informative sampling when learning to forecast treatment outcomes over time. This was jointly authored by our collaborator Toon from Belgium, who visited us for a while, and with his supervisor Wouter. And we presented this earlier at ICML this year. In this paper, we're interested in learning from irregular longitudinal data, because often we don't only have data available where patients are observed at a single time step, but actually multiple time steps. And we might want to forecast entire trajectories of patient outcomes under different treatments. Some recent machine learning work, including lots from our own lab, has considered estimation over time, but has focused solely on the effects of time-dependent confounding. What we argue in this paper is that confounding is not actually the only challenge present in such data. Instead, patients are often observed irregularly and informatively over time. So patients, especially in clinical practice, don't present themselves at random times or at perfectly equally spaced time points, but at irregular and informative time points. And the challenge that we're considering in this paper is learning under informative sampling. In particular, what we did in this paper is expanding the allowed sampling mechanisms implicit in related work. So what's been the focus of most work, implicitly or explicitly, is regular sampling, where basically time series models like RMSN or CRN assume regular time intervals of observation in time series. More recent work has considered what we would call sampling completely at random, where sampling times are irregular but uninformative. And this has been implicitly used in recent work on continuous time treatment effects, including TECD from our own lab. What we consider in this paper is sampling at random setups, where sampling can be informative of some measures, some measurements, but only those that are also measured. So no hidden things are allowed to inform sampling times that also inform outcome. And this is the continuous time problem we consider in our paper. In particular, we note that this kind of informative sampling also leads to covariate shift and means that observational risks are not equal to theoretical risk also here. And there's potential bias when using empirical risk minimization with observational data like this. In particular, the solution that we consider is to use intensity importance weights, where we reweight observations by their likelihood of being observed. And we augment an existing method from our lab developed by Nabeel, TECD, with inverse intensity weights, both in a two-step approach and in a multitask framework, and show that this greatly improves its performance in experiments when sampling is not completely at random. And from this paper, we took away that longitudinal data presents many more challenges than just the presence of confounding-induced data shifts, and different degrees of informative sampling can equally hinder the estimation of personalized treatment effects. Learning in such settings does require strong assumptions on mechanisms for confounding and sampling, and that really makes it tricky. And it would be interesting to relax some of these in the future. So overall, the conclusion from this year has been that the machine learning literature so far is focused on a very narrow set of problems in the treatment effect estimation context, but that in practice, there's a much broader set of challenges that arise. And we think it's time to move our problem settings closer to reality. We are also always curious to learn more. What other neglected challenges are there? The application of machine learning in treatment effect estimation problems. My work is sponsored by AstraZeneca. So we would like to thank our funders for all their support on this. And if you're interested in learning more about our work on treatment effects more general, please visit the pillar on our lab website. Thank you so much for listening.
The second set of 3 talks today, and these are going to be focused around accelerating scientific discovery with AI. And these are going to be 3 very different talks in terms of application, covering pharmacology, physiology, and physics. And so our 3 talks will be given by 3 of our PhD students from the lab, Sam, Krzysztof, and Jeroen. And we're going to kick off with a talk by Sam about generative discovery of equations.
Yep. Hi, everyone. It's a pleasure to be talking today. So as Fergus kind of introduced, so we'll be kicking it off with Unraveling Nature's Laws, Part 1 of Generative Discovery of Equations. So in this brief talk, I'll talk about our recent iClear paper called Deep Generative Symbolic Regression. This is joint work done with myself, my excellent co-author, Jeroen, and my supervisor, Mihaela. So what is symbolic regression? So symbolic regression aims to find a concise equation F that best fits a given data set D by searching the space of mathematical equations. This is a task which is fundamental to scientific discovery. The identified equations have concise closed-form expressions. They thus are interpretable to human experts and amenable to further mathematical analysis. So a good example is in the 17th century, Johannes Kepler, from looking at the elliptical data of Mars, discovered his Kepler's laws, and a process took 9 years to do. Symbolic regression today can automate this discovery task, enabling this same search to take minutes with the tools that we develop here. We'll show that our new technique can achieve new state-of-the-art for large input variables and find these more efficiently, providing a coherent framework to build upon. Symbolic regression and neural network regression are actually two different approaches to modeling relationships within data, and each has its unique advantages depending on the problem at hand. Now, to just briefly summarize why we're interested in symbolic regression is mainly for interpretability. Such a symbolic equation, as the ones you can see here, generates mathematical expressions that can be easily understood and interpretable by humans. This transparency is crucial in fields of engineering or understanding underlying phenomenon, which is important as is the prediction itself, for example, in physics, economics, or healthcare. Also, they have simplicity, so the models can be often simpler and have fewer parameters than, say, a black box neural network method. These can actually lead to better generalization from smaller amounts of data, since model complexity can be closely controlled to prevent overfitting. And also these extrapolate better as well, due to they can actually extrapolate better to the conditions outside the observed training data in the domain, and rather than just interpolate between data points that they may have seen to. Also, actually, as we'll show in this work, we can incorporate domain knowledge as a prior, which is easier to understand domain-specific knowledge into the model by constraining the search space into equations that make physical or theoretical sense. So where can this symbolic regression or discovery of equations be used? For example, it can be used in pharmacology, for example, pharmacokinetic pharmacodynamic modeling of determining concise closed-form equations, in finance, for example, in micro and macroeconomic models, where we're discovering a mathematical equation that represents these, physical laws in physics and all processes throughout physics, and also medical research, such as better models of disease modeling or models of organs inside the body. So what are the current problems with symbolic regression, and why don't we see it widespread in machine learning today? So fundamentally, two limitations prevent the wider machine learning community and I suppose the world from adopting symbolic regression as a standard tool for supervised learning. That is, symbolic regression is only applicable to problems with a few variables, for example, 3 at the moment, and it is very computationally intensive. This is because the space of equations grows exponentially with the equation length and has both discrete and continuous components, as we can see here in an example. Now, importantly, actually, and what is our work? What's the novelty here? So actually, equations are complex objects with many unique invariances, structures that can help guide the search. And we believe that actually good representation is the key to solve these challenges. Now, equations are complex objects with many equation invariant structures, such as commutativity, and these simple equivalence rules can rapidly build up with multiple variables or terms, giving rise to complex structures that have many equation invariances. Importantly, these equation equivalent properties have not been adequately reflected in the existing representations used by existing symbolic regression methods. First, existing heuristic search methods represent equations as expression trees, which can only capture commutativity via swapping the leaves of a binary operator. However, the trees cannot capture other properties such as distributivity. And second, existing pre-trained encoder-decoder methods represent equations as a sequence of tokens, and just as sequences of words in natural language. Now, the sequence representation cannot encode invariant structures, such as here, x1 plus x2 is not equivalent to x2 plus x1, but we actually know that they're mathematical equivalent. So can we do better? And actually, lastly, one is reinforcement learning methods for symbolic regression do not learn representations of equations. That is, for each data set, these methods learn a specific policy network to generate equations that fit the data well. Hence, they need to retrain the policy from scratch each time a new data set is discovered, which is very computationally intensive. So we propose deep generative symbolic regression framework. Rather than represent equations as trees or sequences, GGSR learns representations of equations with a deep generative model, which have excelled at modeling complex structures such as images and molecular graphs. Specifically, GGSR leverages pre-trained conditional generative models that correctly encode the equation invariances. the equations representations are learned using a deep generative model that is composed of invariant neural networks and trained using an end-to-end loss inspired by Bayesian inference. Crucially, this end-to-end loss enables both pre-training and gradient refinement of the pre-trained generative model at inference time, allowing the model to be computationally efficient and generalize to unseen input variables. This achieves state-of-the-art results on symbolic regression benchmarks. So if we look at the architecture now, the key idea is to both use equation and dataset invariant aware neural networks combined with the end-to-end loss inspired by Bayesian inference. You can almost intuitively see this as a multimodal transformer architecture where we actually use a transformer to output the sequence of mathematical tokens and have a extra modality input to encode an entire data set into a good representation. And we pre-train this and then actually use a fine-tuning inference step at inference time, which we'll go into now. So GGSR is the best of my knowledge, is the first symbolic regression method able to perform gradient refinement of a pre-trained encoded decoder model using our end-to-end normalized mean squared error loss. So it consists of two steps. So the first step is a pre-training step where the equation and dataset invariant aware encoder decoder model learns a posterior distribution, which is the probability of the equation given the dataset, PF given D, with parameters theta by pre-training, as we can see here, through a reinforcement learning policy gradient method. The second step is at inference time, we use an optimization method to gradient refine this posterior and a discrete search method to find an approximate of the maximum of this posterior. By sampling this generative model, we can sample equations that actually hopefully fit the data set well, such that we find an equation that does fit the data set well, hence solving the method. So GGSR is, to the best of my knowledge, the first symbolic regression method able to perform gradient refinement of a pre-trained encoded decoder model using our end-to-end normalized mean squared error loss, compared to the existing methods, which are reinforcement learning methods and encoded decoder methods, which we'll actually go into now what they are. So if we look at reinforcement learning methods, they normally aren't able to encode an entire data set, and instead they start with a random initialized network, which then has to search through equations and has to be very expensively trained at inference time when we wish to seek or discover a new equation each time. And this can't actually encode prior knowledge generated or conditioned on an existing data set as well. Whereas existing pre-trained encoded decoder models normally they're trained by cross-entropy loss and trained actually very similar to how existing large language models would be trained. Now, these can't actually encode the mathematical equivalence properties of equations on the output. And these are often trained by cross-entropy. However, what we propose is a unified framework to train both of these together, where we, instead of just use a cross-entropy loss, we use an end-to-end loss and train everything through policy gradients. Therefore, our approach is encompasses the existing approaches in a good way. So the results. So GGSR achieves high recovery rate with more input variables, specifically in problem sets of Feynman D equals 5 and additional Feynman and synthetic data sets. Now, what we mean by higher recovery rate is that the data sets that it's evaluated on in this table are synthetic data sets where we know the ground truth true equation representing the data set, corrupted with noise as well. And samples are taken from this equation, forming a data set, so a synthetic data set, but actually over many, many equations and problem sets. Now, we're discovering the exact equation that has generated this data set, therefore that would be given a correct data set, and therefore averaged over the problem set of equations in this data set, we generate an accuracy of recovery rate. We also detail here the average equation valuations as well, which actually is the number of equations that we have to test on the test data set to see if we found the right equation. And we can actually see our method is much more computationally efficient in the equations that we have to evaluate on the observed data set. Now, the results as well over, there's an existing symbolic regression benchmark called SR bench, which we actually achieved the new state-of-the-art when this work was published in iClear 2023 this summer. So This is a true equation recovery rate on the ground truth unique equations, and we achieve a significant increase in the new state of the art. Now, symbolic regression benchmark is a real-world symbolic regression benchmark, and it consists of 252 diverse regression problems from systems of ordinary differential equations, physics equations, and actually is derived from open source machine learning data sets. It consists of problems that range from 47 to 1 million samples and from 2 to 124 features. And it consists of mainly two sets, so black box regression problems taken from the Penn machine learning databank, which consists of 46 real-world problems, such as observational data collected from physical processes and synthetic processes. Now, these include health, informatics problems, business, technology, environmental science problems, and government problems, and also environmental observation problems and economic market problems. And we also, inside this benchmark, consists of ground truth equations. Now, these ground truth equations come from Feynman's symbolic regression database, which is actually taken from the Feynman lectures on physics and the Feynman equations from there, and also ordinary differential equation repositories as well of observed data sets there. And these ordinary differential equations actually encompass different differential equations such as nonlinear and chaotic dynamical processes. And we can see that we achieve state of the art. So that's quite nice. Now, the contributions and takeaways. So you can now perform symbolic regression on a larger number of input variables whilst using less inference time, computational costs compared to reinforcement learning techniques for symbolic regression. We can correctly encode a data set to start from a good equation distribution, leading to efficient inference, and this achieves state-of-the-art accurate results across symbolic regression benchmarks. Now, this is applicable to pharmacology, modeling, financial modeling, physics, and also medical research and disease modeling as well. Now, we hope this work provides a practical framework to advance deep symbolic regression methods, which are immensely useful in natural sciences. And we hope doing so has the opportunity to accelerate scientific discovery of equations that determine the true underlying processes in nature and the world. You can find out more information with our paper here and code here. And I'd like to say a huge thank you to my sponsor, AstraZeneca, for really making this work possible, and Georgie's sponsor as well, Office of Naval Research. Thank you.
So yeah, welcome everyone. My name is Krzysztof, and today I'm going to show you how our lab advances machine learning for discovering partial differential equations from data. So first, as Sam has already told us, symbolic regression is a branch of machine learning that tries to uncover mathematical closed form equations from data. And today we're going to focus on one specific type of equations, which are differential equations. Such equations contains derivatives, and in particular, we're going to focus on ordinary differential equations, or ODEs. So these are differential equations where the derivative is taken only with respect to time, and partial differential equations where the derivative can also be taken with respect to other dimensions, for instance, spatial dimensions. So why are we interested in differential equations? Because they often are a very good description of important phenomena, such as tumor growth models or pharmacological models, and also epidemiological models. So discovering differential equations has some unique challenges compared to the standard symbolic regression. And to see that, let us consider a standard symbolic regression setting where we want to discover a particular equation. For instance, this is an equation for kinetic energy. We have a data set where we have different masses and velocities and also corresponding energies. And we can formulate the problem as a standard supervised learning problem where the energy becomes the label and we want to find a corresponding function, and we can use standard losses to do that. However, when we want to discover a differential equation, and this is, for instance, one of the Lotka-Volterra equations, our data set consists of trajectories, and we're missing the derivatives. Derivatives are usually not observed. So the question appears how we can formulate the objective without the label. And one idea is to just create a label. So we could just estimate the derivatives directly from the trajectories. However, we don't want to do it for the following reason. It's usually very challenging. So it is especially challenging where the data is noisy and it's frequently sampled. And here the center plot shows the comparison between the ground truth first derivative and three other estimated derivatives by three different algorithms. And we can see that there is quite a big mismatch between those curves. And on the right-hand side, you can see a similar thing happening for the second derivative, where the effect is even more pronounced. And what's important to see is that this problem is much less problematic when we just want to estimate the trajectory itself, which you can see on the left-hand side. And this problem becomes even more challenging the higher the order of the derivative. So our solution in our work Decode, discovering closed form ODEs from observed trajectories, which is authored by Zhao, me, and Mihaela, we propose a different thing, something we call a variational trick, which is based on the variational formulation of ODEs. And to see how it works, we're going to consider the same equation we considered before. And we rewrite it so that we have the dependence on time and everything is on one side. And what we're going to do is we're going to take this equation and then multiply it by a special so-called testing function and integrate through the entire domain. And then the variational formulation of ODEs says that basically the equation on the left side is the same as the following integral being equal to 0 for all testing functions from a predefined set. So then we can multiply this equation, and I want to focus on just one part of this equation. This is the part that contains the derivatives. If we now take this integral, basically what we want to do is to take the derivative from the trajectory onto the testing function itself. And we can do it using integration by parts. This is a standard mathematical technique. And if we choose our testing functions in a particular way, we can even get rid of this additional term. So if we now take all of this and put back into the original equation, what's important from all of this is that at the end, we have an expression when there is no derivative of the trajectory. The only derivative present in the equation is the derivative of the testing function. And once again, if we choose the testing function in a very specific way, we can just calculate it analytically without losing any accuracy from the process. So now this is how we developed our algorithm called Decode that uses this variational formulation to define its objective function. And it consists of two steps. First, we estimate the trajectory, so we denoise it and interpolate it. And then we define the objective using exactly the integral expressions are defined before. And the whole search process through different closed form expressions can be done through any symbolic regression algorithm. And just wanted to highlight that this is different how it's usually done, and this can be seen on the bottom part of the figure, when first the derivative estimated and then a standard loss such as RMSE is used. And we tested Decode in a variety of experiments, and it has much better performance than the methods that depend on derivative estimation, and it's much more robust to varying noise levels, to varying step sizes, also varying sample sizes. And these particular examples I'm showing right now are tested on the Compers model and generalized logistic models, which are models used to model non-linear growth model with saturations. So these are also equations frequently used in science and modeling. But now Decode works only for first order ordinary differential equations. So we can ask, what about higher order ODEs and even partial differential equations, so PDEs? And first, I want to point out that the problem is much more difficult. And that's why in ODEs, we basically have just one kind of derivative. This is the derivative of the trajectory with respect to time. But with partial differential equations, we can have derivatives with respect to multiple different variables. We can also have higher order derivatives. We can have mixed derivatives and even more complicated expressions involving the product of the field and the derivative itself. And this space becomes very difficult to search. That's because the space becomes much vaster. But also what's even more important, this variational trick may not always work, because in our derivation, we used some assumption on how the equation looks like. And with PDEs, this is no longer given. So now let us discuss the assumptions made by the current methods for PDE discovery. And there are two important assumptions that are made by these methods. One of them we call the evolution assumption, and it basically means that the partial differential equations is assumed to be of a particular form when on one side we have the derivative with respect to time, and on the other all of the other terms basically. And what's important to note is that not all equations are of that form. For instance, Gauss's law is not of that form. And the other assumption we call linear combinations, and it basically means that the equation is linear with respect to the parameters. And such equations cannot contain terms like, for instance, sine of the theta times xy, or the exponential of theta times xy, where theta is the parameter, because it no longer can be represented in that form. And this assumption actually severely restrains the space of possible equations to discover. So another question is, can we actually relax these assumptions and still allow for variational formulation so that we can circumvent the derivative estimation and thus be more robust to noise and with varying step sizes and number of samples? And just to recap, the current methods always make the evolution assumption and either assume that the PD has to be the linear combination form, or they work only for explicit first order ODEs. And this is exactly what decode does. And we want to highlight that relaxing the linear combination assumption is not triggered, as not all PDEs admit variational formulation. So how can we do it? So what we do, first we have to remind ourselves that when I was discussing the variational trick, we only focus on one term with the derivative. And in fact, if we look at all the proofs, it turns out that the terms without the derivatives can be as complicated as possible, and it does not change whether the equation admits the variational formulation or not. So building on this insight, we propose the following characterization of PDEs. Any partial differential equation can be expressed in the following form, where we collect all terms containing derivatives into so-called derivative bound part, and all terms without derivatives into so-called derivative-free part. And the significance of the derivative-free part is that it can be evaluated directly from data, whereas derivative bound part requires access to the derivatives. So if we want the PDE to admit the variational formulation, we do not have to put any additional constraints on the derivative-free part. However, derivative bound part still requires some technical constraints for the variational trick to work. And now we use this novel characterization of PDEs to define variational ready PDEs, or VR PDEs, which are currently the broadest family of PDEs that admit variational formulation. And now our task is to search through this space. And this is how we developed the Decipher in our paper, Decipher Discovery of Closed Form Partial Differential Equations, authored by me, Jeroen, and Mihaela, and presented, is going to be presented this year at NeurIPS. And Decipher is an algorithm that searches, that requires no linear combination assumption, no evolution assumption, searches through all closed form derivative-free parts, uses the variational formulation, so it doesn't require derivative estimation, and searches for a linear subspace of derivative bound parts. And we have to search for a subspace of this because searching for the whole space would be intractable. So Decipher consists of 3 steps. In step 1, we have to choose the dictionary of derivative terms to form the basis for the space of derivative bound parts. This usually includes standard partial derivatives of various orders, mixed derivatives, and it can also include the more complicated expressions, such as a derivative of a square of a function. Then we take our data set, and in the second step, we estimate the fields, similarly as it was done in Decode. Then we take our predefined testing functions and compute certain integral expressions involving the derivatives of the testing functions as specified in the dictionary. All of this can be deemed the pre-processing step. And finally, we get to step 3, the actual optimization. Similarly to Decode, we're going to use a symbolic regression algorithm to suggest an expression for the derivative-free part. Then we're going to apply this derivative-free part to the data. And then our task is to find a matching derivative bound part for it. And it turns out we can frame this problem as a constrained linear least squares problem, and we designed a heuristic algorithm that can solve this problem very efficiently. And then we pass this loss path to the symbolic regression algorithm to optimize everything in a loop. And we tested Decipher in a series of experiments as well. And we show that not only performs better on discovering equations that the other methods can also discover. But what's even more important, it can discover equations that are beyond the capabilities of the current methods. And what's shown in the figure below, on the figure on the bottom on the slide, we also show that the variational trick actually gives us gains. So we compare Decipher to the ablated version, where we have everything the same apart from this variational objective, and we see there is a big gap between the two methods. So let me now just summarize what the applications of both of these algorithms can be. So as I mentioned with Decode, it's about discovering ordinary differential equations, which can be useful for tumor growth models, pharmacological models, and even epidemiological models. And then Decipher can be used for even more complicated phenomena. So for instance, for spatial-temporal physical systems, so we can consider equations governing the oceans or the atmosphere, for instance, where some places can actively add or remove CO2 from the atmosphere, and the sources and sinks are likely to be described by a derivative-free part, which Decipher is specially equipped to discover. With population models, they can be used in agriculture to determine the harvest or for pest control to predict their impact on crop. They've also been used in environmental conservation to model the population of endangered species. And in all these scenarios, the rates of growth and mortality are likely to be described with derivative-free part as well. So Decipher is uniquely positioned to discover such equations as an aid to human experts. And finally, epidemiological models are crucial during a pandemic for their planning and interventions. For many diseases, the rates of mortality and infection are actually age-dependent. Thus, modeling the spread of disease using PDEs rather than ordinary differential equations might provide superior results. So we would like to thank Roche for supporting our work, and we would like to encourage you to read our papers and see our code. Thank you very much.
Thank you. So my talk is about causality, which is a bit weird coming after Krzysztof and Sam, but there's actually a very good reason, because Krzysztof and Sam and I have collaborated in figuring out how ODE discovery, as well as other dynamical systems discovery methods, connect to causality. And I already saw a question in the chat, which is somewhat relevant to my portion of this session. So we are particularly focused in this lab in real-world applications. Mihaela made a big call on increasing efforts in reality-centric AI, and causality has always been a bit of a weird duck in this pond, as it's typically not really applied to the real world, right? So causality is very theoretical, it has many constraints, and we wondered how can we connect it to some real world applications. And this is our focus, it always will be our focus. So also for our efforts in causality, we should take this into account. One portion of causality talked about by Alicia earlier is treatment effects, which actually has some real world focus. It's a bit of a different type of causality than what I usually work with. So I work with structural causal models, introduced and popularized by Judea Pearl, but treatment effects, in my opinion, have always been developed with at least some thought on real world impact. Some applications of treatment effects include pharmacology, like drug response models, physiology, where we want to monitor tumor growth, treatment regimes, so coming up with optimal treatment plan optimization, but also methods beyond medicine, like predicting impacts of stocks or some macroeconomic things, policy design, all that stuff. So it really has a really broad real world impact. And in the reality-centric vein, it seems that time is really crucial in many of these real-world scenarios. So the scenarios I listed here are all scenarios that have at least some influence by time. And our lab has been a very prominent contributor in treatment effects over time over the past years. So this is a screenshot of Joanna's paper, which was published a while ago, but it's typically referred to when people want to do treatment effects over time. And I think Alicia also mentioned it in her talk. So most problems actually are temporal. So while there is a lot of work in treatment effects in a static setting, there's much less work for treatment effects in temporal setting, which is weird because given it's fairly reality-centric, we would expect actually more methods in the temporal domain, but that's just not the case. So let's zoom in on one of them. So pharmacology, right? So in treatment effects over time papers, what we see is people test their method in almost all methods are tested in the same synthetic setup. So these are a few screenshots from papers I just Googled, some of them from our lab, but not always. And they always test in using the same ODE, right? So we have a pharmacological model, which was published in, I think, Nature, where people monitor tumor growth, chemotherapy. So what's the impact of chemotherapy and radiation on tumor growth, and some noise, etc. So it's always the same ODE that people use to generate some synthetic data, train the model on, and do some testing given a ground truth equation. That's quite cool and quite interesting. So why do we test using ODEs? Well, because they model a really broad set of real world problems, right? It's a fairly realistic benchmark. It is published in Nature. People do cite this work, so it is quite an important equation, this one. And there are multiple, like this is just one of them, and people test on other equations as well. But for illustrations purposes, I always screenshot the same one. Why then would we learn an inference machine, essentially? Like if we know that this thing is an ODE underneath, why then would we train a neural net, which is, first of all, not interpretable? These equations are interpretable. We are going to learn some model that we cannot interpret. Neural nets typically require a bunch of data, has unnecessarily large hypothesis space. So a neural net can definitely fit this type of equation, but it can also fit many, many, many others. And maybe that's not necessary if we know that our underlying problem lies within this space of problems. And the neural net is only causal by proxy. And I know I'm maybe stepping some toes here, but interventional distributions are baked into the design of the architecture as well as the assumptions that they operate in. So it's actually quite weird knowing that this is a type of problem that we want to solve. Why then would we use this huge model? The key point of this talk and this new area of research that we're developing is that we expand essentially the field of temporal treatment effects by learning the underlying structural equation for the probable interventional inference. So we actually want to learn the structural equation. In this case, we're just using ODEs, but it would extend to PDEs and all those dynamical systems as well, based on the talks of Krzysztof and Sam earlier. But we take a radically different approach to treatment effects and thereby expand the field of treatment effects over time with our framework and our work. So what's the difference between ODE discovery and causality or treatment effects? Well, first of all, we cannot use standard equation discovery methods without some adjustments or considerations. So the methods that Krzysztof and Sam presented, but also other methods, they are quite relevant to causality, but not out of the box. We need to make some adjustments. For starters, ODE discovery methods don't necessarily work on a treatment effects data set. That's because treatment effects typically operate using 3 variables, X being some set of covariates, could be multidimensional, some outcome Y, and some action or treatment A, which we want to intervene on. There are other things that make treatment effects difficult that may or may not work with ODE discovery methods. Regular sampling is maybe a bad example because ODEs, we don't necessarily assume regular sampling. But missingness, bias, all that stuff, it makes treatment effects difficult, and we need to take this into account when we want to apply an ODE discovery method or a PDE discovery method for that matter. So this is exactly the subject of our paper. So how do we connect an ODE discovery method with the machinery of treatment effects to solve essential treatment effects problem using an ODE method? To do this, we provide a general framework connecting ODE discovery with treatment effects. We reconcile the many differences, like the assumption sets, like how to incorporate treatments into an ODE. And using our framework, we propose insight, which is a method that's spewed out by our framework, and apply to a treatment effects model based on ODE discovery and show that it does work in certain settings. In the paper, we use Cindy, which is a very popular method. It's not our method, so it's not biased to our lab. But we could use methods that we presented earlier as well. So in short, how does reconciliation work? So there's 3 steps. The first one is Treatment effects, and that's actually a nice property of the field. We typically list our assumptions very clearly. People who have worked with treatment effects know that I'm talking about consistency, overlap, and interoperability. So on the right here in this column. This is not true for ODE discovery methods or dynamical systems discovery methods. There are some assumptions for sure, right? Like the equation we want to discover is an ODE. That's a fairly obvious assumption, but there are more. We list them out in the paper, and then we informally connect the treatment effects assumptions with the ones made in ODE discovery. So first step in reconciliation then is, are we willing to make these new sets of assumptions? Maybe in favor of the treatment effects assumptions because they do not overlap 1-to-1 or 100%. So there is some mismatch. Our paper shows what considerations you have to take before you actually make a decision on this difficult question. A second step then is, well, a treatment plan typically is discrete or categorical or whatever. It's not necessarily a dynamical system, right? We don't want to administer treatment literally all the time, unless you're on some sort of Baxter, but that's not necessarily the case. How then should we incorporate a treatment plan into a dynamical system, which we want to discover, right? And we give some solutions how you could do this for a binary treatment, categorical, all that stuff. So how can we deal with those? Well, we show you, and you can implement or take this consideration when actually learning an ODE. And then the third and final step is, and this is the interesting one, when you do ODE discovery, so you give some data to an ODE discovery method, and it will give you an ODE. But we have actually multiple patients in one data set, and discovering the same ODE for each patient wouldn't make much sense, right? So the same way you would learn a neural net, you condition it on covariates, and the outcome function is probably different condition on these covariates. And we want to do something similar when we train an ODE discovery method. And the way we do it is we introduce this concept of between subject variability, where the parameters of each ODE method are slightly changed given a different patient. So in the middle of this figure, we'd have a standard treatment effects model, which corrects some bias. In this case, it's covariate shift, and then learns an outcome function given all the samples. That's great. Our method does something different. It doesn't necessarily correct bias because it's not focused on this, but instead learns a different ODE function for each patient in the data set. And I'm only showing 5 functions, but there would be n functions, right, from n different samples. Great, so how do we do? So in the paper, you can see the results are quite nice. I didn't copy them in because it's quite boring. What's actually more interesting is from our 3-step plan. So this is a very simple thing. We built this method called Insight, and it performs really well on a subset of treatment effects problems. As an asterisk, it doesn't perform well on any method, and that is on any data set, sorry, and that is because the assumptions that we make in ODE discovery, in this case, we copied them from Cindy because this is the underlying model, they don't necessarily apply to the data set that we actually want to test Insight on. So if we have a very complicated data set that's not governed by an ODE, we cannot use this. Maybe a PDE is more what you need. So, but that's not actually the main point. Like Insight is nice, but it's not the main contribution. The main contribution in this work, however, is we bridge together 2 completely separated fields. So ODE discovery and treatment effects have coexisted for quite a while, but have never really communicated. And this work is actually some sort of bridge or communication layer between these 2 separated fields. We believe, and I strongly believe actually, is that this idea can really push the causality agenda further. This is a new and completely radical idea in the treatment effects field. And I think by continuing this work, we would come up with some really interesting new models which expand the problem space of treatment effects. I maybe should have copied Alicia's slide into this and showing that we also do the same sort of movement where we increase the size of the treatment effects space. So from the reality-centric perspective, these ideas can push pharmacology, physiology, and many other disciplines as well, because they also bake in ODE methods into their literature. So to connect back to my slide deck previous year, and I'm hoping many people from previous year also attend this year's open house. I presented a new agenda called Causal Deep Learning, CDL for short. This type of work lies at the absolute center of causal deep learning, and I'll show you how. So essentially, from my causal deep learning talk, as well as this paper that we wrote, we learned that we can map causality into this tiny map, where on the left side we have input, we have either temporal or static data, and we learn some representation. And what we learned from this paper is that time is extremely important, as well as learning a fully known structural equation. Actually, learning a fully known equation is pretty much empty, like this in the current state of things. So this final fourth column where we learn a real symbolic equation from a causal perspective has not been explored in the literature so far. And with this paper, with this idea, we want to map or learn from some data the actual known function. So this is the type of, mapping from unknown causal structure through time to a causal structure with a fully known equation is what this paper is about. And in Cindy particular, I believe would be from parametric, so this square, parametric square to time to a causal structure with a fully known equation. And some final pointers. There are quite a bit of online resources on causal deep learning. The paper that I just discussed is still pending on archive, so it will be online soon. And it was funded from my part by the W.D. Armstrong Trust. So thank you.
So our three talks are going to be on AI for human empowerment. And so the first talk, if you'll allow me to pass the microphone to myself, is going to be about large language models. And afterwards, I'm going to pass over to two PhD students from our lab, Jonathan to speak about robustness of interpretability methods, and Alex, who's going to speak about empowering humans with AI collaboration. Here we go. So yes, thank you for being here today, and I'm super excited to be speaking about some recent work about large language models and how we can use them to form a novel interface between clinicians and digital technologies. So over the past few years, our lab has developed a number of new machine learning methodologies and approaches, and you've heard about some of these already today. And while these all represent wonderful technological and methodological advances, ultimately, one of the things we want to do with such models and methods is to use them to improve clinical practice and ultimately to have a positive impact on the healthcare system. So one question we might have is, how do we best use these models? And one strategy that we've adopted over the last few years is to really focus on building what we call clinical demonstrators. And these are typically web-based interfaces that enable clinicians to interact directly with models via a graphical user interface, rather than using an API or some kind of code-based interface. And here is an example from autoprognosis for diabetes risk prediction. And here is another example from our lab for a time series approach for active surveillance of prostate cancer that was published last year. Of course, we're not the only ones who are building these kind of clinical demonstrators. And here is the interface for QRisk3, which is the current recommended risk score for cardiovascular disease in England. And a commonality amongst all of these interfaces is that they allow clinicians to enter the necessary information to run the model, and then to receive as output the model prediction alongside potentially some other information. However, I think there are some pretty significant usability limitations around these clinical demonstrators, and this primarily stems from the fact that they are fixed and non-adaptive interfaces. It's very much kind of a case of what you see in the interface is what you get, and if the information that you're looking for is there, or if you have some related question, it's not possible to obtain anything further than what's already been built into the interface. Of course, we could go back to the drawing board and add further information to interfaces, but there's always going to be some kind of complexity usability trade-off, where the more information that's there, the more difficult it becomes to use such an interface, especially for new users or those with more limited training or experience using a particular tool. So in this talk, I'm going to motivate and present a system that uses large language models to build a new type of interface between clinicians and digital tools, such as the AI and machine learning models that our lab develops. So you might be asking at this point, beyond just the output of the model, what information might you actually want? So I'm going to use the concrete example of risk prediction to discuss some representative questions at different stages of the patient encounter that a clinician or indeed the patient might have. The first is that before even using a new risk score with patients, clinicians might want additional information before they want to use or trust the risk score. For example, which features does the risk score use? Why are these included? How is the risk score validated? And indeed, what's the methodology underlying the risk score? Next, once a patient has arrived, the clinician might want to confirm when clinical guidelines recommend risk scoring, what the recommended risk score is currently, and indeed who the risk score is suitable for and whether or not it's suitable for the patient at hand. Once the models output a risk estimate for the patient, both the clinician and the patient might want further information about what characteristics led to the patient's risk, or indeed what effect changing a specific feature or characteristic would have on the risk. And finally, once we have this risk, clinicians need to determine what, if any, action to take next. And thus, they might want to check what actions recommended by the clinical guidelines based on the individual's risk. So what is the current interaction paradigm? So currently, clinicians interact directly with digital tools, most typically in the form of those clinical demonstrators that I discussed previously. And as I mentioned, this can have limitations, and we're really interested in building a new type of interface. And so I want to briefly discuss some alternatives to this paradigm and how we can integrate large language models to achieve our aim and improve interfaces between clinicians and digital tools. The first option we have is to retain these existing interfaces, but in addition, perhaps allow clinicians to interact with large language models and have conversations. While there might be some benefits to adopting this type of approach, I think ultimately this separation between the large language model and the digital tool is ultimately going to impact the quality of the interactions that's possible. And in fact, actually the functionality of the digital tool isn't really extended in this type of interaction. A second approach is to actually replace existing models with large language models. And while there's been some very exciting developments using LLMs for clinical tasks, including predictions, they're often not the best models to use, in particular when there isn't text data available. And additionally, this neglects the existing digital tools that already exist and are being used in clinical practice today. We therefore chose to develop a third approach in which large language models operate by using digital tools to facilitate interactions with clinicians. Using a large language model enables dynamic interactions that can adapt to the needs of the user and is scalable to multiple risk scores and other tools, and allows the user to query new external information without having to update the language model itself. And perhaps most powerfully, it also overcomes many of the problems surrounding hallucination, since the majority of the information doesn't actually come from the large language model itself, but is going to be provided by the underlying tools. And the large language model is facilitating this interaction by selectively retrieving the right information from the underlying tools and providing it in a natural way to the user. So how can large language models fill this role? As I'm sure most people are probably aware by now, given how much large language models have been in the news over the last year. Large language models are trained essentially to predict the next token based on a large text corpus. And the capabilities of large language models have actually been significantly improved by further training via a process known as reinforcement learning from human feedback. And so as just a quick example of what a large language model might do is that when asked a question such as who is the president of the United States, the large language model will continue on this question and might provide the answer Joe Biden. So let's say in this case, the large language model answers correctly. One challenge for these models is that if the information changes, for example, the president changes, but the model isn't retrained on any new information, it won't be able to correctly answer the question. Another challenge for large language models is reasoning. When presented with more complex questions, such as this maths problem that's shown on the slide, large language models have been shown to perform quite poorly. A number of approaches have been and are still being developed that can encourage large language models to reason, and this significantly improves their ability to perform on these kind of questions. The most well-known approach for this is probably what's known as chain of thought reasoning, which encourages large language models to think in a step-by-step fashion, rather than simply giving an answer straight away. So to illustrate this, to answer this question, instead of just saying 11, the large language model answers with a set of logical steps needed to come up with the answer of 11. This is great, but it doesn't address the first issue I mentioned, which is that large language models kind of only know what they already know. Other work has enabled large language models to take actions within an environment and receive an observation as a result of that action. So I appreciate that's probably slightly abstract, so I want to illustrate this with a slightly more concrete example, and that is like, what is today's date? This changes every day, so how can the large language model know the date every single day? Of course, this information we could just provide as context to the large language model, perhaps at the start of the prompt, but this clearly isn't scalable to many facts and many sources of information. However, instead, the large language model could perhaps take the action of, let's say, the hypothetical action get today's date, and receive the observation that today's date is in fact Thursday, the 2nd of November, 2023. And this was a great breakthrough for answering factual questions, since it enables large language models to essentially just look up answers for things, assuming we provide them with a suitable lookup tool. However, this approach doesn't work particularly well for more complex queries or when we need to retrieve multiple pieces of information. This brings us to a very recent approach called REACT, which stands for Reason and Act, that combines these reasoning and acting steps. And I want to illustrate REACT through a very simple example, but I think which really illustrates this concept well. So the question we might pose for a large language model could be, how old is the president of the United States? So to answer this question, the language model first reasons that it needs to find out who the president of the United States is, and then takes the action to search for the US president, and receives the observation that Joe Biden is the United States president. Based on this observation, it reasons again and decides that it needs to find out when Joe Biden was born. It then conducts another action to search for Joe Biden's birthday, and receives the observation that he was born on the 20th of November, 1942. In the next reasoning step, the large language model decides that it needs to work out how old Biden is given when he was born, and runs this action of calculating the age given Joe Biden's birthday and the current date, and receives the answer of 80 years old. And so then the large language model concludes by answering that the president of the United States, Joe Biden, is 80 years old. For the remainder of this talk, I want to present the system that we've built on top of this REACT reasoning system that has enabled us to construct a new user interface that equips large language models with digital tools and provides a new interface between clinicians and these tools. So I'm going to present two examples, and in this first one is cardiovascular disease risk prediction. For this, we've provided the large language model with access to the QRisk-3 risk predictor, the accompanying publication describing the risk score, and the NICE clinical guidelines for cardiovascular disease. I'll now play a short video demonstrating this.
In this example, we will demonstrate how large language models can provide a novel interface for cardiovascular risk assessment. We'll begin by providing the data for our patient John. For simplicity, we're providing this as an external file, but this could also be collected via a web interface if desired. We then ask for our patient John, what is his 10-year risk of developing cardiovascular disease? The large language model understands our question and uses the QRisk tool to calculate the risk for John, which estimates that his risk is 13.3%. Now suppose that the clinician notices that corticosteroids are included as part of the risk score, but isn't sure why this is the case. Instead of searching through the scientific literature, we can ask the LLM. Using the Show Source Information button that we've implemented, we can see that the model queried the QRisk paper to obtain this information, which helps prevent hallucinations and enables clinicians to check the source of the information that's being provided. Finally, the clinician would like to know what, if any, action should be taken next given John's risk. The LLM searches the NICE clinical guidelines for cardiovascular disease, risk assessment and reduction, and reports that the guidance is to recommend lifestyle changes, specifically saturated fat reduction, replacing saturated fat with monounsaturated fats, as well as exercise, and regularly reviewing their cardiovascular disease risk.
So for the second example I want to present is for diabetes risk prediction. And in this example, we used a diabetes risk score produced from the autoprognosis package produced by our lab. And we also equipped the large language model with the ability to interpret the model using SHAP values. So I'm going to play another short video demonstrating an example conversation with a large language model equipped with these tools.
In this example, we'll demonstrate a large language model-based interface for diabetes risk prediction. Again, we begin by providing the data for our hypothetical patient John. For simplicity, we'll provide this as an external file. We then ask for John's 5-year risk of developing diabetes. In this example, we're using a machine learning risk score for diabetes, developed using the autoprognosis package. The LLM uses the autoprognosis model together with the data provided and returns a risk score of 0.4%, suggesting that John has a very low risk of developing diabetes, which makes sense given John's normal HbA1c measurement. One of the major challenges with the use of machine learning models in clinical practice is engendering trust with users. To facilitate this, we've enabled the large language model to use methods from explainable AI to understand the predictions of the risk score. When asked which features were the most important for John's estimated risk of 0.4%, the LLM returned the most important features used by the model, including a graph displaying the Shapley values. Unsurprisingly, HbA1c and age were two of the most important risk factors. Additionally, the other three most important risk factors were blood-based biomarkers, namely serum gamma-glutamyl transferase, C-reactive protein, and cystatin C. All three are known diabetes risk factors, giving some level of confidence in the prediction of the model. Finally, we can use the large language model to answer specific questions from clinicians that might not apply to all, demonstrating the benefits of a dynamic interface. In this case, the clinician asked for more information on the explainable AI method used, Shapley values. The LLM used its background knowledge to briefly explain that Shapley values are a feature attribution method and that this method originated from game theory.
So thank you very much for listening to my talk today about how large language models can help form a new interface between clinicians and digital tools. If you're interested, please do see our paper for more information. Or if you actually want to build your own interface, we've released all code necessary to build your own interface with new digital tools.
Okay, hello everybody. Very nice to be with you today. So I'm going to use the time I have to discuss this work about evaluating the robustness of interpretability methods. So before that, maybe a small introduction. So my name is Jonathan, and I'm a third-year PhD student at the Vandershire lab. And I'm really interested in interpretability, robust machine learning, and recently I've also become, as many people, are very interested in generative AI. So if any of these teams is of interest to you, please reach out in one of the social medias here. Always happy to discuss these teams. Okay, so let's talk about the agenda for my talk today. So I'm going to start with motivation and outcomes of the work I'm going to discuss. So like a general picture. And then, of course, like discussing this in detail will require to brush up some background work. In this case, we're going to talk about geometric deep learning, which is the formalism that I use to define robustness of interpretability methods. And this is going to allow us to define our own contribution, which is a definition of explanation invariance and equivariance. How can we use these two metrics, explanation invariance and equivariance, to evaluate the robustness of interpretability methods? And finally, how these measurements with real data allows us to build a set of actionable guidelines on how to use interpretability methods in a robust way. So let's start with the first point, and maybe a general context first. Why do we care about interpretability at first place? Well, if everything works well and interpretability methods are faithful to the model, we could at least use them for three things. The first one is to allow the machine learning models, to make ourselves, humans, smarter, because these models probably have learned a lot of interesting things. And if we can unpack this knowledge from the model, then it's very valuable for us to learn a couple of new things. A second thing, I guess, is by looking at what the model has learned, sometimes we might be unhappy with some biases or like some bugs that the model has developed at training time. And we might want to go back at the model and fix that. But before doing that, we need to identify these bugs. So interpretability can be a very, very valuable tool to that end. And finally, and I guess that's very important in AI, a very important problem in AI is keep humans in the loop. We don't want AI that take over the world without interaction with humans. We want to kind of monitor these AIs. And I think interpretability provides very, very valuable tools in order to do that. So I guess that's a dream, but in reality, interpretability methods might not completely be faithful to the model. And actually, I would argue that's probably something that keeps a lot of researchers in interpretability awake at night, is the risk of actually misinterpreting the model by having something that's not in line, by providing explanations that are not in line with the true behavior of the model. So to illustrate that, I'm going to take a very visual example first, and bear with me, I'm going to go to like more medical examples later in the talk. But let's take this very simple image of a shirt here. So I can train, like a machine learning model to predict what's on the image. And if the machine learning model is trained pretty well, it's going to recognize that there is a shirt with a high probability P here. So that's a prediction for the model for this image. And I can ask the model to explain, like why this prediction. And like the example that Fergus showed earlier, I could, for instance, ask which features are important for the model to localize, to understand that there is a shirt on this picture. And I can use, for instance, a method like integrated gradients or SHAP to see which pixels of the image are the most salient to identify that there is a shirt on the image. So all good right now. Everything seems to be doing okay. But like what I can do is take a very simple transformation of the image and see how all of these things change. So in this case, I've taken exactly the same shot, except that I've moved the shot slightly on the image. I put it a bit more upper left on the image. And of course, if my model is trained properly, or is going to, and it has the right inductive bias, it's still going to see that there is a shirt on the image, and the probability is not going to change because the shirt is exactly the same. So the model's prediction is not affected by this transformation of the input. On the other hand, if I take the explanation now for this new input, I can see that the feature importance, on the other hand, has changed during this process of moving the image slightly, which is something quite unexpected because the model makes no difference between these two images. So you expect the explanation to be consistent with this insight. And I guess this is exactly what we want to avoid, is having explanations that tell us something that's different from the true behavior of the model, which in this case we know because we have this inductive bias that we have injected inside the model. So if I try to unpack this in a bit of a more formal way, we have interpretability methods that should be valuable, that should actually be faithful to the models if we want them to be actionable and useful in practice. So if a model has a property that we can call P, then the explanation E should be consistent with this property P. And the property that we're going to study, motivated by the previous example here in this paper, is models that are invariant, or we can say robust, to group of input symmetries. So transformation of the input that conserve the information inside the input. And this is formalized by the fact that, like I can transform this input X into X prime, and the prediction of the model is going to be completely unaffected by this transformation. On the other hand, and so if that's the case, I expect the explanation for the input X prime to be equivalent to the explanation for the input X as well, which is not what we observe on the previous slide, of course. So I guess that leads us to the first outcome, which was kind of illustrated by the example on the previous slide, but which we're going to see is like a general trend, is that there are popular methods like gradient SHAP or TCAF, for instance, that are inconsistent with the model symmetries. So in other words, the model encodes some symmetries and the explanations don't reflect the symmetries of these models. And of course, that's something we want to avoid because we don't want explanations that behave differently from the model. And the way to avoid that, we propose, in order to avoid that, we propose a set of guidelines, 5 guidelines that are easy to follow and actionable, that guarantee you that the interpretability methods you're going to use are going to be consistent with the model, at least with respect to the group of symmetries that are encoded with the model. And an example of such a guideline would be like something like that. Gradient-based methods should be used with invariant baselines in order to be robust to symmetries. Okay, so let's actually brush up some background work to make this a bit more precise. And the background work that's relevant here is the very interesting line of research that's done in geometric deep learning. And in this domain, in this work, the first thing you need to define is a domain, is actually the support on which the data is defined. So if you take an image, for instance, a domain is a grid. The grid is going to be populated by pixels, but if you want, like the domain is actually the skeleton on which the data is defined. And if you take graph data, of course, the domain is the graph skeleton. So this defines the domain on which data is going to be supported. So now, of course, the data that we are playing with, images or like graph data, is going to assign to each point of this domain a number. So for instance, if I take an image, it assigns a pixel to each of the cell inside the grid. If I take a molecule, for instance, it assigns an atom type to each node in the graph. So we have made the transition from the domain, the skeleton, to the signals, which actually represent the data that we use to train our machine learning models. So what's interesting to us here is symmetries within these input signals. And the symmetries are kind of are formalized as group that preserve the information inside the signal. So for instance, a symmetry for an image could be a mirror symmetry. And if I take a mirror symmetry of this image, I obtain a new image that has the same pixels, but like swapped based on the mirror symmetry. And for graph, for instance, that could be like a graph automorphism. So for instance, if I take 2 atoms of water and I swap them, I obtain a new molecule of water. So the molecule signal is conserved by this transformation. And the idea is that these group symmetries are actually implemented in practice by using what we call group representations, which are just matrices that tell you how this transformation acts on the input signal. And the idea, I'm not going to go into details, but is that signals are actually vectors, and symmetries are represented by matrices that act on this vector. And the transformation of the input signal is just implemented as a multiplication of a matrix, of this vector by a matrix. And so what we are interested in is actually functions that take these signals as input, because machine learning models are just eating signals and spitting predictions. And we are going to consider two types of functions of these signals. The first one are invariant functions. So those are basically functions that don't change when you apply symmetries to the signals. So if I take my previous example of images, I can count the number of blue pixels on this image, and that would be 4. And I can do that again after transforming the signal by applying a mirror symmetry, and that will still be 4. So the number of blue pixels is actually an invariant function of the signal. And the second type of function we're going to consider in this paper are equivalent functions. And those are functions that transform as the input signal. So they follow the same transformation as the input signal. So for instance, I could take the position of the blue pixels on the image. And if I do that, I will have the blue pixel on the first image. And I can do the same for, I can localize the blue pixels on the transformed image, and I will have the mirror symmetry of the first image. So the position of the blue pixel, in this case, is an equivariant function of an equivariant function of the group of symmetry. The group of symmetry being the mirror symmetry, of course, here. And this might seem a bit abstract, but this actually describes a lot of architectures that people use in deep learning. So for instance, convolutional neural networks are invariant to a group of translations. Graph neural networks are invariant to node permutations. And you can find a lot of examples like this. So in this paper, the models we are studying are always endowed with such symmetries. So they're always invariant to a group of symmetries, that we know in advance. And so once we have that, we can actually extend this definition of invariance and equivariance to explanation themselves now. And the way we do that is by simply taking explanation as itself a function of the signals. An explanation takes a signal, for instance, an image, and assigns, like a vector, like for instance, a feature importance saliency map to the image. So it actually eats signals and spits explanation. That's what an explanation method do. And the explanation method in a similar way can be invariant to the group of symmetry. So for instance, I can take my previous symmetry, just moving the shot on the image, and I can take the most similar training example before and after applying the symmetry to this image. And if my explanation method is actually invariant to this symmetry, this most related training example is not going to change if I apply this symmetry to the first image. So before and after applying the translation, the most related training example to the image remains the same. And there are also like equivalent explanations, so which are in this case transforming as the input signal itself. So an example of an invariant an equivalent explanation would be a good feature importance method. And the good feature importance method, again, would draw a saliency map to explain the prediction of a classifier. And after applying the translation, the saliency map will follow exactly the same translation as in the input. So in the case of equivalent explanation, the explanation itself follows the same transformation as the one you apply to the signal. And of course, like those are two desiderata that you would like to see in different cases. And we introduce metrics in order to see when these desiderata are fulfilled in practice. So there is an invariance metric that ranges between -1 and 1, and an equivalence metric that also ranges between -1 and 1. I'm not going to go into details of this definition, but basically you want these metrics to be as close to 1 as possible in order for the explanation method to respect the symmetry encoded inside your model. Of course, you have to pick one of the two metrics in practice. So as we have seen, for instance, in the previous slide, invariance is the right metric to use if you have an example-based explanation method. And equivariance is the one to use if you have, for instance, a feature-based explanation method. And there are other examples, of course, that we cover in the paper. So basically, I'm going to go quickly on that, but we use that to evaluate a lot of different feature importance, example importance, and concept-based methods. And we produced, and we actually studied that in very, very different settings. So with time series data, graph data, point cloud data, images, and text. So we have covered quite a big spectrum in the modalities of machine learning. And what we found is that there is systematically good players and bad players in the different explainability methods. So for instance, here you see that integrated gradients and deep lift are usually robust, follow the same symmetries as the models. And there are some methods like gradient shap or feature permutation that typically underperform according to these metrics. And we also study cases where we have slightly relaxed symmetries, but I'm not going to go into details of that for today. And yeah, we extend this analysis to example-based methods and concept-based methods. So please read the paper if you want all of these details, but that's too much for me to cover in this talk. So I'd like to finish maybe with a set of actionable guidelines that we derive from that, and with a scenario, that's kind of a scenario you might find yourself in if you're, for instance, a practitioner using machine learning model with interpretability methods. So imagine you're a cardiologist that uses a machine learning model to detect abnormal heartbeats. And this machine learning model is staring at this image here and seeing that our heartbeat seems abnormal. And now you want to probe this model and to see, does this model actually use some medical concept that I'm aware of? For instance, does this model know about supraventricular heartbeats? So you want to probe the representation space of this model in order to see that. And you use a method like TCAF in order to do this. And you know that this model is invariant to time translation, meaning that, for instance, if I take this heartbeat here and I translate it in time, like the prediction of the model remains the same. The heartbeat is still abnormal. And of course, you want to make sure that the explanations you are going to give with this TCAF method here are going to be faithful to this invariance property that is encoded inside your model. And what we provide for you in this case is a set of guidelines in the form of a flow chart that provide this guarantee, that makes sure that you can use your method and your explanation method is going to be consistent with the symmetries of your model. And let's actually follow like an example of this flow chart. So imagine you evaluate this invariance metric that we provide on this example X, and you see that this invariance metric is not equal to 1, meaning that your explanation is not robust to these symmetries. Then your flow chart will give you an explanation for why that happened. And in this case, you can see, for instance, that you are using TCAF in a non-invariant layer of your model. And our flow chart will typically recommend you to use TCAF after a pooling layer, for instance, if you are using a convolutional network or a transformer. So know that, of course, you can go back to TCAF, so the method you're using to probe your model, and use it in a better way and in a more informed way in order to produce explanations that are consistent with the true behavior of your model. Of course, that's only a small chunk of the true flow chart, but I don't have time to discuss the whole flow chart. So please, if you are interested in this, follow one of these links here and check our paper. And also, like if you're interested in interpretability in general, you can follow this link on the right here. That's my website. And I share a lot of thoughts and papers on this about interpretability and other subjects. With that, that's the end of the talk. So I thank you all for your attention. And I think I will hand over to Fergus again. Thank you very much.
Thank you. Yes. So hi, I'm Alex. I'm a fourth year PhD student here with Mihaela, working on imitation learning and inverse reinforcement learning for understanding decision-making behaviors. As part of our quantitative epistemology agenda that we've very, very loosely talked about with some of the language model stuff we've been doing. But now I'm going to talk about an agenda of empowering humans with AI collaboration. So really taking all of the machine learning that we've seen so far and allowing that to kind of be placed within a setting where humans are interacting with it and using it for decisions, and how we can do that kind of optimally or in some way improved just having results. And this is joint work with another PhD student in the lab, and obviously Mihaela herself. So obviously we've heard a lot today about all the great ways we can use machine learning to improve predictions, analysis, interpretability and understanding and discovery. But obviously we know that machine learning is not a kind of perfect science at this point. And in important domains like healthcare and other safety critical areas, we know that machine learning really shouldn't just be used to replace humans. We know that they have kind of very common failure modes, where they can be currently very overconfident and generalize poorly, and kind of importantly, make mistakes that are actually surprisingly obvious to domain experts. And thus, can't really be trusted to just be deployed and make decisions in important situations where they could potentially do damage to people. But on the other hand, as we've seen, we also know that they are kind of superhuman at understanding subtle patterns that we can't detect. And as such, definitely are able to kind of make useful and informative decisions in cases where we may or not be sure. And there's a kind of tension there that we're trying to understand and overcome. And so, we believe we need to really focus on designing systems that are able to guide interactions between these machine learning tools that give us recommendations, as well as the humans who are ultimately going to act on these recommendations, and potentially have very significant impact on people's lives. So we're going to consider a kind of general setup where there's a protected environment that only the human decision maker is actually allowed to act in. So we're not going to let machines make any decisions. However, we do have humans with access to some decision support models that is maybe our best attempt at getting a correct action, but something we're going to be very aware of is that we know that sometimes this is not going to always be correct, and we may need to ignore the decision support model at appropriate times. And these are often the models we may have seen so far, including treatment effect predictors, or time to event stuff, or any just predictor of an action that we should take in a setting. So now we're going to kind of focus on what we're going to describe as the meta system, which will guide the interaction between the human decision maker and the support model in useful ways, and hopefully can lead to things like teaching, correcting ideas, allowing the human to be more introspective of their decision-making system, and hopefully allowing us to get the right balance between the human making the decisions when it absolutely knows the case, and when it's a bit sure, or feels like it's a setting that the support model might be able to do very well, is able to in some ways defer to them. And hopefully this kind of combination is just going to improve our ability to do effective decision making in these safe environments using machine learning, empowering humans. So past work in our lab has focused mostly on understanding the human. So the human is making decisions, we've seen them acting in an environment, and we want to understand and think what they're thinking about when they make decisions. Why? So that we can maybe go to a second stage where we can then go, okay, well, we can now design our machine learning support systems that will complement the way that the humans are thinking about it. And for example, we've done this in Alzheimer's diagnosis with adaptable decision tree policies that go over time, as well as belief space models. Here, for example, with our decision trees, we're trying to extract the decision tree that we think that the human is acting on over time, where it might change dynamically. The reason being for this case, for example, when we ask clinicians a lot of the time, they come back to us and they say that the best way to describe the policies that are used in medicine is often a decision tree, simply for reasons such as interpretability of explaining this to new doctors who are learning, as well as there being a kind of a reasonable amount of accountability and transparency in this kind of architecture. We can say, if something, then we will do this, and it's very easy to go back and inspect this, pass it on, and relay it if something goes wrong. And it's obviously very useful if we can extract that perfectly. Well, if we could extract it perfectly, it'd be great, because then we can say, well, it looks like you were following this flow chart, where if the hippocampal volume was low, we might go to try and do an MRI, and then if that comes back clean, we just kind of continually think you're kind of in a healthy zone, but actually maybe the normative guideline is that we should be doing an MRI anyway. And so if we can then be like, okay, it looks like there's a discrepancy between what the kind of GMC Council guidelines are to what it looks like you're doing, that might be something a teaching moment at least for those clinicians. And we've got other kind of models, maybe a bit more abstract, where we're trying to model the belief space of the clinician, whether they think that the patient is healthy, whether they've got mild cognitive impairments, or are kind of classified as a kind of dementia patient, and how their belief updates between kind of actions and observations. But all this, of course, is just focused on understanding the person. We haven't really gone at this point to actually improving their ability to make the decisions that they are doing in this environment. And that's what we've looked at recently with what we call closing the loop. So coming back with, well, we've sort of understood you a little bit, so let's try and improve what you're doing, and we can maybe kind of over time improve both our machine learning predictions and also the human's ability to act in this environment. So we can maybe we've done a bit of work looking at a maybe more restricted setting, where we're trying to build a system that learns which explanations are useful for a human decision maker, and thus we are able to kind of optimally aid the decision maker by showing them only the explanations that they kind of find useful to understand a support tool that's given to them as well, with the high kind of aim that then with this kind of personalized explanations given to them on top of a decision support tool, they will be able to kind of more accurately and more efficiently make decisions. This is kind of obviously built on the fact that there's a huge number of explainability methods, a lot of which Jonathan has talked about just a moment ago. But then within the literature, there's obviously a kind of a huge disagreement over which ones are kind of potentially useful and in different settings. And it often changes depending on the task at hand or also the person who's actually using them. And as we've seen, they've obviously got their own problems with equivariance and invariant explanations. So we need something to kind of help people use these kind of tools. So in this work, we basically build the meta system, which takes the human acting in an environment and the support model, which is just a black box function, as well as a set of explainability methods, and try and learn through interaction which ones the human decision maker finds the most useful, and thus improves kind of the overall ability of the system. And the way we do this, I mean, we won't spend too long exploring exactly the kind of the method, but in principle, this is all through repeated interaction with the environment. So we take an environment where a human picks an action, the support model then suggests an action. The meta system, which we're mostly concerned about, selects personalized explanations based on the context as well as the person and the history, and provides that to the human, who then makes a final action that may or may not be different to the suggested action, and obviously the initial action. And through this repeated loop, we do approximate Bayesian inference over some model of the human behavior. So like in previous work, we end up specifying a model of how the human is thinking about all these decisions, and then doing approximate inference over this model, which is updated over time as they continually see and act differently. Now, obviously, the difference is we then use this model to each time step take an action ourselves, i.e., which set of explanations do we show a clinician or the decision maker. And this is obviously done partly through a kind of RL-esque algorithm that uses a Thompson sampling based on our posterior distribution to give some optimal explanations. Now, concretely, we kind of set up an experiment with human decision makers, classifying images in order to kind of test this. So this was actually done on the CFAR10 data set, which is a kind of common machine learning benchmark for image classification, which has like kind of low quality, low res images of a variety of different categories, trucks, planes, cats, dogs, these sort of things. And it's actually kind of quite challenging. There's a subset of them which is actually quite challenging for humans to actually pick out what they are. Now, obviously, this is like a relatively toy example. So just like close your eyes and imagine you're looking at some radiology scans and we're trying to pick out which patients have got cancer. And maybe we'll get closer to kind of more reality-centric medical application. But essentially, in this case, we are presenting people with these images, asking them to classify it, and then giving them the prediction of a neural network, as well as one of 5 explainability methods. For example, we use the simplex, which Jonathan developed last year, as well as some nearest neighbor, deep lift, occlusion maps, and integrated gradients, as they kind of represent a few different types of explainability methods that are out there. An important thing to note is we actually give the neural network predictions, but the neural network has been specifically designed to not be an oracle network, right? It's not always going to give us the right answer. In fact, its accuracy is only about 50% on the test set that we give to people. The idea trying to be like, even with a kind of suboptimal machine learning algorithm, we can still raise the performance of the human, because the areas where the humans and the machines are getting correct answers are different, right? They're good at different things. And so even though on average, the machine might be worse, it will actually provide useful explanations and useful decisions in a certain subset that humans are not able to compute. And we can see this in our improved accuracy. With humans at 72.5%, like just base, we actually kind of improve to about 84%, given access to our algorithm as well as the machine learning system, which, like I said, on average is only 50% accurate. We can also see that we actually kind of outperform other baselines, like just kind of giving them the random explanations, as well as asking the person beforehand, which is your favorite explanation, and giving them that one. And we showed them with an example of the explanation methods and how they might be used, which just goes to indicate, I think, a lot of the points of what is actually useful in the interpretability methods is not always what people are expecting, right? They might see integrated gradients, for example, and think, okay, that's quite nice. It's highlighted the areas that the model is thinking it's a burden, and that's kind of interesting and kind of helpful, and I agree with that. But when it comes to actually helping people make decisions, like either to convince them that this machine learning system knows what it's talking about, or that it, on the other hand, doesn't. You could be looking at prediction and thinking, well, I don't think that's right. And then you see the explanation method, and it confirms to you that, yeah, the machine learning system has just kind of completely lost the plot. I don't want to listen to this. I want to go with my own gut. That information from interpretive method is not obvious when you just look at it, and we kind of need to find out through interaction with them. We can also see we learn an efficient personalized ranking preference quite quickly with our method, and we also show that when we show them what we believe are their preference algorithms, preference explanations rather, they end up on average viewing a much fewer explanations, because they don't have to click through all of them to find out the one they find useful. We show them one they find useful first, they go, okay, great, and move on. Now, interestingly, you actually also see a decrease over time in the number of explanations shown with our random subset, which is odd given there's no change in the algorithm over time for that. And so we probably think it's actually mostly to do with fatigue, right? People are doing a classification task and they're getting a bit bored, and they're just like, okay, well, I'm just going to start skipping through explanations, not really taking it seriously, even in just this kind of 50 to 70 examples. So you can only kind of imagine how this is going to happen at scale for kind of someone's job that they do every day. So it's important for us to give them the information they want quickly, so they don't get tired and bored of the task. So, how can we use these techniques? I think there's something to highlight here is that it doesn't really matter what the task is. Our method for selecting explanations is actually completely task and model agnostic, right? It doesn't need to be image classification. It could be a language model question. It could be a tabular data prediction. As long as you have a task that a human can do with a machine learning predictor model, as well as a set of explanations, we can apply it. And it's got very minimal computational overhead compared to the the prediction model themselves, as well as the explanations, since I'm just doing kind of approximate Bayesian inference over time with some kind of Monte Carlo sampling. It's actually kind of relatively simple and relatively low dimensional. So, this could work in settings even just using this as a kind of co-pilot for your kind of decision-making systems. We can just wrap this around any existing machine learning system to hopefully improve performance. Great. So obviously there's plenty more ways that we can empower humans with machine learning. This is just one example. And so obviously if you're interested, please reach out. Here's my email address. And yeah, I'd just like to say thanks specifically to MSR for kind of sponsoring this, my work in general. Thanks very much.
Awesome. Thank you so much, Alex. And thanks everyone who gave a talk today. I think that now brings us to the close of today's open house session. So I'd just like to say a massive thank you from Mihaela, myself, and all of the Van der Schaar lab for you attending today if you're able to do it, but more importantly, your support more generally for the lab. We'll be hoping to put today's session online very soon. So if you missed a particular talk, or if you've got colleagues you'd like to share this with, we'll send details soon and make sure you're able to do so. And so with that, thank you very much and look forward to speaking with you soon.